So we have the pleasure to welcome Thomas Kirchartz, who, as you know, has been here. I think you have been here in all Landsberg seminars. Am I correct?
You are absolutely correct, yes.
Thomas Kirchartz, he is at the Forschungszentrum Jülich.
Yes.
But before, spent a period at Imperial College London. Started off, I believe, in thin film organic solar cells, and now he's very active in Perovskite, of course. So, Thomas.
Okay, thank you very much, Tom. Very glad to be back here in Prague. It's always a very nice experience to come to these Landsberg seminars and to give these talks on fundamental problems in photovoltaics. So I also want to send regards from Uwe Rau, who I think some of you may know. He's now retired for a couple of weeks now, since 1st of March. And he also wanted to come to the seminar, but got sick before he came. I've now slightly modified the direction of my talk, so I'll also cover things that I think he would have liked to present to you if he could have been here today. So it's also a bit of a continuation of the last talk I gave here, I think, in early October 2022. The topic is about quantifying recombination. That is non-radiative recombination via defects. Yeah? So it does exist despite the defect tolerance. It's not going down to zero, but also extraction of charge carriers in these Lead-Halide perovskite solar cells. It's a close collaboration between myself and Uwe, and Lisa was the PhD student working on this over a couple of years. So the key challenge that we wanted to look at in these materials is to have a variety of characterization techniques, and each of these techniques could have, let's say, one input. It could be photons, voltage, current, or any combination thereof. There would be an output, something that you measure. Yeah, so it could be, again, a photon. That would be a luminescence-based technique. Could be voltage or current. Then you might measure it with an oscilloscope or something like that. And then there exists a whole zoo of different methods that are a variant of this. Yeah? So you can have the photon in, photon out type of technique. That would be photoluminescence. And then you can have all kinds of variations. And the reason why there are so many techniques in this whole zoo is that you can do everything in steady state, in time domain, and in frequency domain, and then you can do each combination of input and output, and then you have a whole lot of different techniques. And these techniques I call essentially optoelectronic characterization techniques that we use in thin film photovoltaics and also specifically in perovskites. And what my group is primarily doing is we are taking these techniques, applying them to perovskite and also organic solar cells, and we're trying to develop better methods to analyze the data that comes out of these techniques. And this is what I want to discuss with you today. Well then, in most of the talk, we're looking at this particular technique here, transient photovoltage, which is one of those. So it's essentially photon in and transient voltage out. Okay, so the overarching question of how to analyze data that comes out of these techniques is interesting for me for specific reasons that I want to motivate now. So in many situations, there are two extremes that you can use, two extreme ways of analyzing the data, and none of them is particularly satisfying for various reasons. So when you have, for instance, such a transient photovoltage measurement, then at the end of the day, what you get out on an oscilloscope is a voltage transient. Yeah, so it is a stable value at the start. It goes up, it goes down. And the easiest thing would be to use the purely empirical approach to data analysis. And it's just fitting an exponential to it. Yeah. The problem with this approach, it's the easiest, of course, is that once you have that exponential fitted to the data, what you do next? Yeah, could say that's the lifetime, or that's the whatever. Just give it a name. Yeah, and then you can do a little bit of hand waving and say that means blah 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 blah, and then we write the paper. Yeah, so this is one approach. It's obviously not totally satisfying, but it's quick and it has also its values, I'd say. Yeah. Then the other extreme would be, yeah, okay, I mean, we have a model for it. The model is essentially 3 coupled differential equations with boundary conditions. We can solve them numerically, throw them at the data, and then we've replaced the physical experiment with a mathematical experiment. Yeah. Then we have maybe adjusted a complicated model to our data. But then trying to find out what really happens then becomes a mathematical experiment trying to figure out what on earth these equations are trying to tell me and what their fit or lack of fit to the data is really meaning. Yeah? So the question that then often comes up in this field is there anything in the middle? Yeah? So ideally what should be in the middle, it would be nice if it was intuitive, yeah, so the human could understand it and not only a large language model. It should be comprehensive, yeah, it should tell me something, and it should be sufficiently accurate that it's not like a wild guess. Yeah, it should be better than a wild guess, yeah, in terms of interpreting the data. And I want to show you how to get to the point of having something that works for the middle in this specific case. Okay, so the measurement method, that's a description or a schematic of the setup that we've been using. The setup can do essentially 2 types of measurements. One is transient photoluminescence, one is transient photovoltage. And the red parts of the setup are used more for the photoluminescence and the blue parts for the photovoltage. And some of them are used for both. So essentially you need our sample, solar cell, this case. We need the pulsed excitation, that's this laser here. And for the transient photovoltage, it's a small signal method. We also need a bias slide, and we will later change the bias slide over a wide range of light intensities. And then the oscilloscope would be the thing that we need to measure the voltage transient. If you wanted to do photoluminescence, we would also need to have some detection unit for the photoluminescence. Okay. So now I want to briefly show you what can happen if you use the purely empirical approach to data analysis, which would mean we have some decaying observable. Yeah, could be luminescence, that's the most frequently used one. And then we derive a lifetime primarily by just fitting the data. Yeah? Exponent minus t over tau times prefactor. And then we get this tau out. We could call it a lifetime. And then we can try to find out whether it makes any sense. Yeah? In order to try to find out whether lifetimes reported in the literature make any sense, we did this exercise, Lisa and myself, trying to take lots of papers and then trying to find only those papers that had at least 2 lifetimes reported. That was the challenge. So, and the 2 lifetimes reported, one of them was supposed to be a purely optical lifetime, a photoluminescence lifetime, and the other lifetime was supposed to be an electrical one where an oscilloscope was used for the detection. And that was therefore done on a cell. Yeah, the lifetimes from PL were primarily films, and that was primarily cells. Yeah, which means it's a different thing. Yeah, but it's not a completely different thing. Especially the lifetimes from cells. From cells here should, in principle, always be lower in a way than the lifetimes from films, because there's more recombination going on in a cell than in a film. Yeah? You have all these interfaces that lead to additional recombination. So in principle, you'd expect it to be worse. Yeah? But then when you look at the literature, then each of these points here, Yeah, let's take this red point, for instance, would be one paper where people reported 100 nanosecond PL lifetime and say 200 nanoseconds transient photovoltage lifetime on a cell. Yeah, that's fine. Yeah, that makes, I'd say, reasonable sense. Yeah? But then there were also papers where they reported something like this. So what does that mean? That's kind of, now I have to go straight. So that's 2 microsecond or 3 microsecond PL lifetime. But it's also 2 or 3 milliseconds transient photovoltage lifetime. Yeah? So how on earth could you get like 3 orders of magnitude difference between these lifetimes? And what on earth do they mean? And can they both be lifetimes? So that was a question that we were busy with a couple of years. That was 2021 is when we made this figure. And the abstract problem can be summarized in this slide. So the question is, what's a lifetime? So you can approach the problem from 2 sides. Yeah. On the left, you could approach it from the perspective of a model. Yeah. So model could be an equation that you find in a textbook, is for instance this Shockley-Ritval recombination rate. Yeah. That thing here. Yeah. So you find that in many semiconductor physics textbooks, and it's got 2 taus in there. This tau and this tau is called the electron and hole lifetime. Maybe can say Shockley-Ritval lifetime to make sure people know it comes from this kind of methodology, and they're supposed to be inversely proportional to the density of defects. That's the topic of the last lecture from David, and some prefactor that I call beta N or P capture coefficient for electrons and holes. Okay, good. So this is approaching it from a model, and the other way of approaching it is from the observable. Yeah, from something that you can measure. So that could be from the PL or the transient photovoltage or whatever. Yeah? And the problem or the underlying topic of this talk is that this is not always the same thing, yeah? For a lot of different reasons. And I want to show you a few simple examples of how to approach this problem of what the lifetime from a certain observable means. And this is now done for the specific case of transient photoluminescence. So we're not yet at the photovoltage, but still at the slightly simpler case of transient photoluminescence. And so let's start with an intrinsic semiconductor. We learned in David's lecture, it's difficult to dope these halide perovskites. So very often they behave in spectroscopic experiments as if they were pretty intrinsic. And you could then say, okay, the differential equation that you could write down to describe the decay of the photoluminescence would be something like this, where you have a dN dt, change in electron concentration, is equal to minus the recombination rate. And the simplest thing would be to have a linear term via a defect and a quadratic term for radiative recombination. Yeah? So this term, despite the defect tolerance, this term will never be 0, always be something happening there. And then if you try to work out what then n of t would be, yeah, and do, say, n of t times p of t is proportional to luminescence, the result will look like this, yeah, for different values of tau n plus tau p as indicated here, 2 microsecond, 500 nanosecond, 100 nanosecond. And then you can try to work out what the effective lifetime of this decay would be at every point in time. Yeah? So how could you do that in practice? So you'd have to work it out from the logarithmic derivative of the luminescence as a function of time. So it would be something d ln luminescence dt, yeah, with a minus in front of it, and minus 1 here in the exponent to get the units right. And you can also express that in units of n. Then it would be, again, a logarithmic derivative of n. So it would be dt d ln n, or n over dn dt. Yeah? And this is now an interesting solution, because this you can work out directly from the differential equation. You don't even have to solve the equation for n of t, you can just work it out from what we have here. Yeah? So what this says is essentially just get rid of one n, get rid of all the minuses, and then invert the equation. Yeah? So if we just do this here, so we get rid of one n each. Yeah? So we get rid of the first n, get rid of the second of one of the two n's for the n square here, and then invert the thing and get rid of all the minuses. Yeah? So that means then we're getting to here. Yeah? 1 over tau n plus tau p, the n is gone, and the kn square got a lost one n to get kn. Yeah? And this is now essentially the effective differential lifetime that we are getting for such a decay. Yeah? Which means essentially, if we plot this now as a function of time, at short times it's continuously changing because this kn term is dominating, and at longer times it's saturating to the value set by tau n plus tau p. So that means in this simple example we can see that the observable would indeed produce exactly this sum of the Shockley-Hall lifetimes if we wait long enough. Yeah, so that means the end of the decay would fit, and the beginning of the decay would not fit because there would be this quadratic term which changes things. Okay, so far so good. And now we will go to devices, and in devices things get unfortunately a bit more complicated because we have more effects that can happen at the same time. Yeah? So it's not just different mechanisms of recombination, but there are now also effects that are not recombination at all that can happen. Okay, now this transient photovoltage experiment is a small signal experiment, so that means we are starting from a certain bias condition at open circuit. So we illuminate it with a bias light, we have a certain open circuit voltage, which is in this case here, it's say 1.18 or 1.19 volt. And then on top of that, we put a laser pulse and see what happens. And this is now a video. And in this video, the laser pulse will be on from 1 to 2 nanoseconds. And here you can see the time running. Here you see what the Venn diagram is doing. And here you see the blue is the Fermi level splitting, essentially. And the red is the external voltage, and there will be a red point that you'll see that will be showing up in the video. Okay. Now, so this is now, the laser pulse is on now, yeah, and when it hits 2, it goes off. Yeah? See the Fermi level splittings go up here. Now the laser pulse is off, so we are at the maximum of the Fermi level splitting, and from there on, the Fermi level splitting is going down, while the external voltage, which is the distance between the red line here and the blue line here, that's still in the process of increasing and increasing and increasing, because it takes a while until the electrons have gone out and are starting to charge up the external electrode. Yeah? And at some point, the Fermi levels here and here will be flat, and then these two, internal and external, will essentially decay together down. Yeah? So we have certain different phases in this transient. So we see in the internal voltage, there's essentially only a decay to be seen. Yeah? But in the external voltage, the thing that the oscilloscope is measuring, yeah? There we have 2 time constants at least. 1 time constant for the rise, 1 time constant for the decay. The time constant for the rise will definitely depend on how easy it is for the electrons to go out. The time constant for the decay will have probably something to do with recombination. Okay, now how do we get this information out? So this is now, before was a simulation, this is now experimental data of the internal voltage derived from a small signal transient photoluminescence. External voltage is from the oscilloscope, measured at the same time on the same sample. And we see here this rise, and then them decaying together. Okay, now the question is, how do we analyze this? And now the decision that we made was to try to find a model that's slightly simpler than a full transient drift diffusion simulation, but that is still all components that we need. And these components are recombination, extraction, and some sort of capacitance of the electrodes needs to be involved at some point. Okay, so call it two-component model because it will be two differential equations. And the two differential equations are, one is for the absorber, and one is for the voltage at the external contacts, which is what the oscilloscope is seeing. Okay, so there will be two coupled differential equations. The first one for the absorber, so we have the NDT, okay, then two terms with a minus for the recombination. Then there will be one term with a plus, that's for the bias light. The plus G is just the bias light. And then there's this complicated looking term, also has a minus here. Then there is some prefactor, S exchange is just the speed of the electrons and holes going out. D is the thickness. And then we have this big bracket here with N minus this thing where we have the external voltage coming in here. This is essentially a term for exchanging charge between absorber and electrode. Yeah? So when N is bigger than that, it's extraction. And when N is smaller than that, or the voltage is bigger than the internal voltage, then it's injection. Yeah? Then injection dominates. So it can do both in and out. That's very important. Okay, and now for the electrode, we have a second equation that says dVx dt, so what the oscilloscope sees. And that is essentially this term here, but with a plus now instead of a minus, because that's what goes out, now appears with positive terms here. And then, because this is in N and this is in voltage, we need to translate from charge to voltage, and the translation factor is the capacitance, or the 1 over the capacitance. And this is this C. Area means it's something in nanofarad per square centimeter or so. Yeah? So it's capacitance per area. Okay, good. And now, what do we do next? Yeah? Now we've already, I mean, it already looks like we are screwed because it's way too complicated now, right? It looks terrible. And at this stage, I thought, yeah, we could have just taken drift diffusion, wouldn't have been much more complicated. But it turned out that now, this now took years from now to something that I liked. Yeah? There were a couple of steps that one could take if one only knew that it would be a clever way to do it like that, that really simplified things. Okay. The first step is just cosmetics. That's getting both equations having the same unit. Yeah? I translate that from N into Fermi level splitting or internal voltage. That's just changing the units a bit, not changing anything with the physics. And then now there's a jump. So there's several steps in the calculation missing. Now I linearize the problem because it's a small signal measurement. I can essentially just Taylor expand all the equation and only take the linear term of everything. Yeah? So I can get rid of all the nonlinear terms. And then I can write it like a matrix equation, yeah, to try to make it an eigenvalue problem. And that can make it very simple at the end of the day. And so what I do here is I now have two equations that always start with a time derivative of either the internal or external voltage. And that is equal to a matrix, 2 by 2 matrix of the internal or external voltage. The delta means it's small changes around the bias condition. Yeah? Okay, and the matrix now contains all the different things that can happen in our little solar cell model. So these two terms are the recombination, the S exchange over D, that's always the extraction term, and all the terms that have an NQ in there. These are the terms, NQ is just an abbreviation of unit carrier density, where the capacitance go in. Yeah? All the NQ terms are charging or discharging the capacitor that is created by having metal electrodes or ITO electrodes on either side. Okay, Now, next step, if we have a problem like that, there will be a solution for v int of t and vx of t, which looks like this fundamentally. Yeah, so just look at the blue delta vx of t. Here will be a prefactor times exponent minus t over first time constant minus the same prefactor exponent minus t over a second time constant, and one of the two time constants, the longer one, will be the decay, and the shorter one will be the rise at the end. Yeah? So they're already called like that, decay time and rise time. Okay, and these two time constants will just be the negative inverse eigenvalues of the matrix, yeah? Which Maple tells you in 5 seconds what they are. And what Maple told us was that that's the two eigenvalues. Yeah? And now the k's are just abbreviations for the different things that are in the matrix. I'll explain them in a moment. But the thing what you see if you just look at this here, yeah, it essentially just looks like the solution of quadratic equations inverted. Yeah? And one of them has the plus square root, yeah, that's the rise time, it's the blah 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 plus square root blah 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 square minus something, and this one is blah 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 minus square root of blah 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 squared minus something else. Yeah, so it's in principle it's something that we used to from school. It just looks a bit complicated, and I hate square roots. Yeah. Okay, so the K1 is essentially, now it is the inverse time constant for recombination, the K2 is the inverse time constant for extraction, and the K3 is the inverse time constant for the involvement of the capacitor. Yeah. Okay, good. At this point, we were still stuck because we thought that set equation looks still absolutely terrible. What to do now? Yeah, and why does the equation look so terrible? Because yeah, you can't do a lot with square roots. Yeah, can't simplify them really. There's only one thing you can do in that situation, and that is, in my opinion at least, you can Taylor expand the square root. Then the square root is gone. And that actually works remarkably well in this particular case. Yeah. So what we did here, to go from there to something useful, we just Taylor expanded the square root, and then lots of things cancel out, and then it gets reasonably simple. And that fits really, really nicely to the data. I'll show you in a moment. Okay, now this is the experiment. So here you see linear time axis, and then the excess voltage axis here. And it's a methylammonium lead iodide solar cell, and these are different bias light intensities, and here you see the associated DC open circuit voltage that we get at every bias light intensity, and then it's nicely color coded. Lisa did that, not myself, and here you can see for each of the color codes, just have to see what the two time constants are that were obtained by fitting the data. Yeah, so this is how a typical fit looks like. Here's some oscillations on the curve, but you can still fit them roughly, and then get the two time constants out, and you can plot them as a function of the open circuit voltage. So that's just an implicit axis of bias light intensity. Okay, good. So you can see they have certain characteristic shapes. So this is more or less S-shaped, while the rise time is pretty constant at 150 nanoseconds or so. Okay, good. Next step was now to try to make sense of these time constants based on these Taylor expanded versions of the inverse eigenvalues. And so this is now how it looks like. So it's significantly simpler than before. So this complicated equation with the square root and so on ended up just being the sum of 3 terms, and the third term was not important. In this case, it was just 2 terms that were relevant. And the first term was just the time constant for recombination. That's the green thing here. And the second, the yellow term was the product of the time constant for recombination times this NQ over N bias term, which leads to such a time constant. And that time constant is the cause of all evil in data analysis before, because that time constant, you have to imagine it as the electrode capacitance trying to discharge itself via a diode. And the diode is the solar cell, the absorber of the solar cell. Yeah? And because a constant resistance, constant capacitance multiplied with a exponentially voltage-dependent recombination resistance that gets higher and higher and higher the lower the voltage is. Yeah? So a diode becomes more and more blocking the more you go towards short circuit. Makes this RC time constant of this effect go longer and longer and longer and longer. Yeah? So that means if you want to discharge a capacitor via a diode, at the beginning it goes fast, but the more you go towards 0 volt, the more blocking the diode becomes, and then it becomes nearly infinitely long to discharge your capacitor versus a perfect diode. And that's why this time constant goes up. It's extremely dangerous in data analysis, this time constant, because it does scale with recombination. Yeah? It's linearly proportional to the recombination lifetime. So if you have two samples with different degree of passivation, then this time constant will totally move along. It will show the right trends that you want to see. Just the absolute value makes no sense whatsoever. It's nothing to do with recombination in the absolute value. Okay, the rise times had also two time constants. The nice thing about this is it's like in electrical engineering you have series and parallel connection. Yeah? So series connection is just adding the terms up, the resistances, and here for the rise time you need to add up the inverse time constants and then invert the result. Yeah? Which means that the rise time is always lower than each of the components that it consists of, while the decay time is always larger than each of the components that it consists of. That's the key difference here. And the rise time has two contributing terms. The first one is just getting the electrons to the contact and the holes to the other contact. That's the D over S is the time constant, and S over D is the frequency, essentially. And the second one is to discharge the electrode capacitance via the resistance of the transport layer. So that's essentially an RC time constant, where the C is the electrode capacitance and the R is the voltage-dependent resistance of the electrode and hole transport layer. Okay, and the combination of these two gives you a relatively constant rise time in the 100 nanosecond range. And now we can say we have now three effects, essentially, and two of them matter in steady state, and one of them is just annoying. Yeah? And so of the three effects, the two that really matter for the functionality of a solar cell in steady state is recombination, which is bad, and extraction, which is good if it's fast. Yeah? And the annoying effect is everything that is capacitive. Yeah? Because capacitance only matters when you have a dV dt. Yeah, so capacitive charging, discharging currents are always C dV dt, and if the dV dt is 0, then it doesn't do anything. Yeah, so that means in any steady state situation, I am not interested in them. And so what I can do now is I can say, okay, what I'm interested in is essentially the recombination lifetime and the extraction lifetime, and in particular, their ratio is decisive for the functionality of the solar cell. And they're related to the decay time and the rise time, but there's always a factor there, this 1 plus NQ over N bias in this case. And here it's 1 plus N bias over NQ, the opposite. But in each case, I can correct for it, yeah? Assuming that the electrode capacitance is really a number and not a function of voltage. And then I can try to calculate back this extraction lifetime, which is then essentially this flat line. No, sorry, it's this dashed line here. and the recombination lifetime is this dot dashed blue line here. Yeah? And then I can divide them by each other, which should be, no, maybe here, no it's not. Can divide them by each other, and then I get a figure of merit for how likely it is to collect my charge carrier, so some sort of collection efficiency. So it's not dividing them by each other, but taking the recombination lifetime divided by the sum of the two lifetimes, recombination and extraction. And the higher that is, the more likely it is to actually collect the charge carriers rather than them recombining before they can be collected. Okay, and this is a quantity for this specific cell. It was in the 95% region for lower voltages, and then at some point it drops down here. Okay, and then we can have a look what that does for the functionality of the solar cell. So go now full circle back to solar cell performance, and in order to do that we essentially derive the steady state version of our two-component model that we had before. Yeah, so get rid of all the time derivatives and try to work out what the current voltage curve would be within the logic of this model. And when you do a bit of math, then eventually you arrive at this equation here, which is essentially a recombination generation model, where you have one term for recombination, one term for generation, but here you have the external voltage in. Yeah, and the recombination rate essentially not depends on the external, but on the internal voltage. So in order to get there, we had to work out what the relationship between internal and external voltages at an arbitrary bias point. And it turns out that the correction for this difference essentially ends up being leading to this prefactor tau r over tau r plus tau exchange here. And this is now an equation that within the logic of the model, which has many assumptions, of course, does make sense. And we can now apply that to our data. So we can take essentially can assume that this factor is 1. Then we would get the yellow curve here. Or we could assume it's whatever we measured, then we get the blue curve here. And the blue curve fits reasonably to the JV curve. That looks nice, but there's one more thing that we did in order for it to really match, because otherwise it wouldn't have matched, and that is we needed to allow for an extra series resistance. Yeah? Because series resistances are something that are not in the model. Yeah, the model is really looking at all extraction losses that occur within our semiconductor up to the electrons hitting the silver and ITO. And all the additional series resistances would add more losses, which we had to account for. So this is a bit cheated, of course. But at least it shows that it's not completely impossible, that the method does make sense and can go full circle back to the device. Okay. Now, to the conclusions. So the first take-home message is that all these transient or frequency domain small perturbation measurements on solar cells, including perovskite solar cells, contain at least 2 time constants. In perovskite solar cells, they contain usually 3 time constants. One is very slow for the ions, and then there should be at least 2 electronic time constants. One of them for the rise and one of them for the decay in this specific case. But it can also be, for instance, if it's impedance, it wouldn't be rising and decaying. There would be something else happening. And it's sometimes difficult to find all the time constants in the data. Okay, and then in all the small perturbation situations, you can linearize the problem, and then the time constants would then follow from the eigenvalues of a matrix. And for this to make your life easier, you need to kind of limit yourself to 2x2 matrices. You can do it with higher order matrices and make the problem more complicated, but then the eigenvalues get so terrible that you haven't really won so much, I guess. Yeah, then it's still still a complicated model. But with 2x2 matrices, and then a bit of fantasy with the Taylor expansion of the square roots, it can end up being a simple, much simpler solution that is much more intuitive and comprehensible than say full drift diffusion. And in principle, the approach works for all types of small signal measurements, so it doesn't have to be transient photovoltage, it can also be impedance, intensity modulated photocurrent, photovoltage spectroscopy. All kinds of things can be done with this general approach. Yeah, and the key assumption is that you can break it down into, let's say, internal voltage and external voltage in this example. So if it's two components, it gets much easier. Yeah? If your Fermi level splitting has a strong function of x, for instance, then you haven't won much. Then you probably have to do the full drift diffusion Poisson formalism. Okay, that's all for me for today. Thank you very much.
So much for an interesting, very clear presentation. Over to you.
Yeah, thank you. Thank you for a nice talk. So you just mentioned here the diffusion of ions. Mm-hmm. So from that I understood that we can get rid of diffusion of ions just by focusing on fast part of the decay. Is that?
I think in frequency domain measurements, it's easier to see because it's so nicely separated in frequency where the different effects are happening. But also in some of the transient techniques, you can see the ions starting to have a strong signal in the more in the millisecond range. Yeah, so at longer times, not at the. I mean, here the innovation was primarily looking at the shorter time scales of these rises. Yeah, these rise times here. So there, I don't think the ions are doing that much.
And another point, of course, we may worry about Auger recombination. That one we can also skip because.
Yeah. So I mean what I haven't talked about today, but I could have talked about it a little bit, is what happens at in transient photoluminescence, for instance, at very high carrier densities and short time scales. Yeah, and there could be that's where you would like to find or would expect to find Auger recombination. Yeah, so what we see is that we find there signatures of diffusion primarily. Yeah, so then this is the range where the x-axis in our samples starts playing a strong role because the mobilities are not infinitely high and the carrier density is not created homogeneously. And these effects, we see them in a slightly different experiment where we look at the spectral shift of the photoluminescence as a function of time. Over the first tens of nanoseconds after a laser pulse hits the sample. And I think there that's a strong effect, and I think it would be very difficult to find Auger below this effect. Yeah, maybe if you try to do the experiment in a certain way, but I don't think it's the most crucial thing, Auger. Because it would matter if you really go to above 1 sun, I guess, then it would matter. But I have never really looked at that so far.
Maybe one more question. Of course, one would just measure intensity-dependent PL. Do you have some experience with that? Do you see? Because I think it's quite. I can imagine you can see all kind of things. But have you ever tried this?
I mean, we do intensity-dependent steady-state PL, but not much above 1 sun, and then I don't think you really see it very well. And in transient PL, we go much higher than 1 sun, but there we don't see something that could not also be explained in other ways. So it's difficult to find something that is very clearly Auger. I think it's working.
Oh, thank you. Very nice talk. It's elegant, I think, way of presenting things. I have some questions. Maybe I'm not sure. You say it's a small signal. In what sense is it a small signal? Because you have a voltage, which is actually like 200 millivolts. So maybe it's small as compared to total VOC, but I guess carrier concentration would change a lot.
Yeah, it is. So this was also some of our worries. So how the measurement is typically done in the literature is that people are trying to stay within 10 to 20 millivolt of external voltage amplitude. Yeah, and this is also how we performed the experiment. You can see that the 20 was kind of the target here. Maybe, or at least to stay below 20. But when you look at the internal voltage, it's not. Here. Yeah, this is of course huge. Yeah, so internally there's a huge effect. So that means that the Taylor expansion of the quadratic term is maybe a bit bold. Yeah. But I think at that point we still went ahead with that problem. Yeah, so I think the Taylor expanding what happens externally, okay, yeah, but the nonlinear term inside the kn squared, ooh, that's not small. Yeah, that is true. So in principle, it would be quite difficult. You'd have to make this very small, but then you have to also understand that this experiment was done. It had the most important motivation for this first experiment here was to even see both the PL and the external voltage. And the measuring small signal PL is really, really difficult. This has only been done once in this paper here. And there we thought, okay, forget about small signal for the moment. We just need to have something where we see data at all. Yeah. And then I think for the future, I would try to go to very small external amplitudes and forget about the measurement of the small signal transient PL.
I think then maybe, if you have a factor, if you are 20% or 50% off on your time constant, maybe it's not so dramatic, as you've shown in that. Sometimes it goes on log scale. So I was more concerned with the impact that it has on the carrier concentration inside the device, which has changed. Huge changes, and then it's non-linear. So maybe, but I don't know.
No. I mean, this is true. So you're essentially assuming that the carrier concentration is given by this value here, and in fact, it's temporarily up here. So it means if you were to analyze this decay, and the quadratic term is important, then it would give you a wrong value for k. Yeah, and this wasn't really our main motivation, but yeah, I agree with you that would cause problems.
I have maybe a last one thing is, I think it's very interesting the way you present things. So you have a capacitance that you could in principle extract, and that is the time constant for the rise. Okay, it's involved in if I understand correctly. Okay, this is NQ term. Yeah. Have you evaluated that quantity?
Yeah, I mean it. So it made sense. It was in the tens of nanofarad per square centimeter. Can't remember whether it was 20 or 50, but it was on this. This is what you would expect when you look at the permittivity and thicknesses.
It's just the capacitance of the depleted device.
Yeah. So I mean, it's a good question. Let's see I need one figure again. So this figure maybe, yeah. So these devices have a peculiar property. This is around 300 nanometers. This is around 30 or so. So factor 10, let's say, between absorber and transport layer, and also factor 10 in permittivity between 3 and 30, which means that the capacitance of the absorber layer and the capacitance of the transport layer would be the same order of magnitude or even very similar. So that means it fits to whatever, but it's not discriminative in the way that it can say, okay, that must be the transport layer or that must be the absorber layer. I think the working hypothesis was that it's the transport layer that is the source of the capacitance. That we have the two transport layers, each of them has a capacitance. They're in series, and that is then the total capacitance that dominates the system. But if the absorber layer also had a let's say geometric capacitance, then it wouldn't really have changed the number by an order of magnitude, maybe a factor of 2, and then that would be very difficult to say given all the other uncertainties.
But on this time scale, you should have mobility should appear somewhere?
Yeah, so the idea is, so this specific model that we had here assumes that the mobility is in the S exchange, but that's the mobility of the transport layer. If you wanted to have a mobility of the absorber layer, it would be very difficult to do that, yeah, because then you need to have a V int of X and T, and then you need, then you're already dead, then you need to do full drift diffusion. Yeah? And yeah, in another recent paper that I got the proofs today for that, I can send it to you when it's out. It's already an archive. Actually, there we looked at also the mobility of the absorber layer and whether the collection losses are rather from the absorber or from the transport layer. And result was it's quite similar. Yeah? So the absorber layer mobility is always lower than you think, and the losses are small. Both of them are small because that's how the sample was probably optimized implicitly, yeah, to make sure that nothing is limiting the extraction.
Thank you. When you defined your kinetic equations, transport equation, and these two coupled equations, you avoided holes. Why is it possible?
Yeah, I know. So the idea is that we have a perfectly symmetric system. So that means that whatever happens for the electrons and the electron contact would happen very symmetrically and in exactly the same way for the holes. That means the model assumes that the sample is also optimized in such a way that hole extraction, electron extraction are not extremely different. Because yeah, exactly. So this factor of 2 here assumes that the system is completely symmetric and that half of the external voltage is trying to get the electrons out and half of the other half is for the holes. And the fact that this is n over tau and not something more complicated assumes that the holes are also n over tau because n is equal to p inside the absorber. Yeah. This is of course also an assumption. It's based on the relatively low doping densities that we always find in these spectroscopic experiments. But of course, there are, for instance, no shallow traps in this specific model. Yeah? So this is something that one could start to add, but then you've destroyed symmetry already, because you then have to decide whether it's shallow close to the conduction or shallow close to the valence band, so it gets a little bit less pretty.
Sorry, I have one more question. What do you think about transient photocurrent decay? Because people start to measure this recently.
Yeah, so we also tried to write down a matrix for transient photocurrent. In transient photocurrent, the bias, so if you do it as a small signal, that is, yeah, then the bias condition would be, say, some steady state illumination. Then you probably do it at short circuit. And then you look at what an extra laser pulse would do in the additional short circuit current that flows out on top of a bias short circuit current density. Yeah? So if this was the the experiment, then it would follow a very, very similar logic. You could write down a matrix that looks very similar to the one you've seen, but you are lacking the voltage as a parameter. You only have the light intensity, but always at short circuit. And as far as we could see, this degree of freedom is not as helpful as the voltage as a degree of freedom. And so we get relatively flat time constants as a function of bias light intensity, and that makes it difficult to discriminate what you're seeing. So that means in terms of choosing a nice experiment, we're trying to choose experiments where when you plot the time constants, yeah, like here, as a function of whatever variable you have, that there's something happening there. Yeah? So if these two were both flat lines, yeah, then it would probably be quite difficult to tell what you're seeing. I mean, the fact that this has this S shape is very telling. That helps you. This is the one thing that helps you to nail down what the capacitance is doing, to really actually quantify the capacitance. And if you didn't have that, a lot of the rest of the story wouldn't have worked out. Yes, you wouldn't have been able to analyze that if you didn't have that. And so in TPC, we are, this is kind of what's kept us from writing a paper about it. We thought it would be a paper that says not as nice as that.
Thank you very much. Maybe